Welcome back, everyone. In this video, I will be continuing the section on limits at infinity. The number 3 here, we want to do the limit as x goes to infinity of the square root of x plus 3x cubed over 2 minus x. Now, anytime you have a square root when you're talking about a limit, you have to make sure the value you're going to, or at least if it's infinity, really big values are in your domain. But what we want here is we would want the inside of the square root to be positive if x gets really big. Now you could just imagine if you plugged in like 100 for x, this would be a really big number. You would get 100 plus 3 times 100 cubed. So this will be fine. Now if I ask this to go to negative infinity, it might not be fine. But this one is fine. And how do we do it? Well, we're actually not going to do it any differently than the way we did this problem or the previous one. We still want to divide by the largest power of x. The problem is the largest power of x is less obvious when you have radicals. What is the largest power of x here? Well, it's probably easy to look at this and say x cubed, but the problem is it's in the square root. So that's not really the largest power of x. If we divided everything by x cubed, what would happen is we would either forge it and it would not work, or we would be doing improper steps. We might be lucky and get the right answer, but ultimately we would be doing something wrong. So the way it works, the largest power of x, you do have an x cubed, but it's inside a square root. So the largest power of x, it looks like it would be this. It looks like it would be the square root of x cubed. Now you want to make sure that your largest power is actually the largest power. So how do we know this power is bigger than just x? We know it's definitely bigger than the x inside the square root because x just has a smaller power than x cubed. Well, remember that the square root is the same thing as the 1/2 power. And when you have exponents like this, when you raise exponents to exponents, we go ahead and we multiply them. So this is really x to the 3/2. And 3/2 is bigger than 1 because this exponent's 1. 3/2 is bigger than 1. That means this is the largest power of x. So what we want to do is divide everything by x to the 3/2. Now what I'm going to go ahead and do is mention that even though we're dividing everything by x to the 3/2 outside of the radical, outside the square root, we're automatically going to shove what we're dividing on the top that's not in the square root into the square root. So outside the square root, it's x to the 3/2, but inside the square root, we would divide by x cubed. Okay. And the reason for that is exactly because the cube root of x is x to the 3/2. And it'll hopefully make more sense when I actually write down the steps. So let's go ahead and do it. We want to do the limit as x goes to infinity. Now for the purposes of this one, I'm going to do the bottom first because it's not in the radical. We want to divide everything by x to the 3/2. We get 2 over x to the 3/2 minus x over, oops, that's not 3/2, over x to the 3/2. All right, so we've got that. Now what about when we're inside the square root? Well, because the x and the 3x cubed are inside the square root, we have to leave them there, but they're also attached by a plus, which means we can't break it apart. Well, what I want to do is I want to shove dividing by x to the 3/2 in here, but when I do that, because I need to keep it balanced, it's actually an x cubed. Right? If I was to take the x cubed out of the square root, I would get my x to the 3/2. That's exactly what this is saying. The square root of x cubed is the same thing as x to the 3/2. When it's inside the square root, we leave it as x cubed because it's equivalent to this. All right, so I hope that makes sense. But once again, it's coming from right here. And maybe one extra step to really explain it is that if I take this numerator, I'm not going to rewrite the problem over here, but if I take the numerator, x over x cubed plus 3x cubed over x cubed, instead of simplifying this, if I wanted to break out the x cubed, well, the first step would be to common denominator. It's already there. So we got x plus 3x cubed over x cubed. Now this is in the radical. And then when we take it out of the radical, we know we have to do the square root of it. We can split up the radical, x plus 3x cubed over the square root of x cubed. And this is exactly x to the 3/2. So really what we're doing here, I rewrite that. Really what we're doing here is we're actually dividing the entire radical by x to the 3/2, which is the same thing as dividing each part. But I wanted to go ahead and shove it in. And when we shove it in and break it up into each part, that's where the x cubed is coming from. But in general, when we deal with radicals, I'm going to do it directly like this. All right, but now we want to do what we did before, simplify, cancel out. So this x over x cubed, one of the x on the top cancels out one of the x on the bottoms, leaves us with x squared. Or it's probably just write 1 there, just remember there's a 1. In here, the x cubed and the x cubed directly cancel out. In the bottom here, we have 2 over x to a power, nothing cancels there. And then x, we can cancel out with x to the 3/2. How much is left? We know this one's bigger, and it's bigger by 1/2. 3/2 minus 1 is 1/2. All right, so let's go ahead and I'm going to write down what we're left with before we try to use our limit properties. On the top, we've got the square root of 1 over x squared plus 3 divided by 2 over x to the 3/2 minus 1 over x to the 1/2. Now you might be wondering at this point, well, if this was a whole number, I would know what to do, because our rules say if we have x to a whole number, a positive whole number in the denominator, then it's 0. Well, it still works if it's a fraction as well. The main thing is that we can't say if this was going to negative infinity, if it would work. The reason why we couldn't say that would necessarily work is because if this was going to negative infinity, then we would have a negative, really a negative square root, which would not work. But since we're going to positive infinity, everything is fine. So the idea is you still distribute the limit. You can bring the limit inside the radical, and then you can do each part. But for the radical on top, I want to go ahead and just break it down. So for the limit, we can distribute it to the top. And we can bring it inside the radical. We get the limit as x goes to infinity of 1 over x squared plus 3 divided by the limit as x goes to infinity. We do it to the bottom. 2 over x cubed divided by 2 2 over x to the 3/2 minus 1 over x to the 1/2. So 2 over x to the 3/2 minus 1 over x to the 1/2. And now, just like we were saying before, this is 0 because x is in the denominator. This is 0 because x is in the denominator. And also, this is 0 because x is in the denominator, even though it's in a square root. Okay, so what are we left with? Oh, and then the limit of just a number is a number. So what's left inside the square root is 3 because we have 0 plus 3. And what's left on the bottom, it's actually 0. So what's going on here? What do we have? Well, the question we had before was when we divide by 0, we know this is plus or minus infinity. How did we figure out whether it was plus or minus infinity before when we were doing limits? Well, we had a number that we were doing the limit towards, and we just chose a really close number. Now, for going towards infinity, we can't necessarily choose a close number, but what we can do is choose a number that's really big. So to pick between plus or minus infinity, what we do is, since the limit is going towards infinity, we plug in a very large x value. To our original here. And if we plug in a really large x value, if it's positive, then it's going to be positive infinity. If we plug in negative, it's going to be negative infinity. So let's go ahead and figure that out. Grab Wolfram Alpha here. And we've got the square root. Let's just do 1,000. That should be plenty big. 1,000 plus, oops, if I could type it in, and then I keep hitting backspace, plus 3 times 1,000 raised to the third, divided by 2 minus 1,000. And you see we get a negative number. We know that it's going to be negative or positive infinity, so you don't have to worry about the quantity. If it's not big enough negative or positive to you, just add a 0 to the end of all these thousands. So now it's 10,000. If you still don't like it, then keep adding another 0 until you're comfortable with saying, okay, it looks like it's going towards negative infinity. But eventually, I guess Wolfram Alpha gets tired of doing big things. You'll see this is just for 1,000,000 because I added in some more zeros. It's negative something, but that's telling me that it's going to be negative infinity. Right. So our limit here is going to be negative infinity. And I'm just going to write equals negative infinity here to specify we got it down to here. And then we realized it was negative infinity based on what we were plugging in. Right. So, definitely more complicated than the first one. Remember also, for the purposes of us, usually when we talk about limits at infinity and we get an infinite number, we don't necessarily care. So also D and E would be usually what we write. But I wanted to make sure I explained that you can still figure out if it's positive or negative infinity. It's normally we just don't care which one it is, so we write D and E. But if we had to specify which one it is negative infinity. All right, number 4 here. This one is a little challenging. We want to do the limit as x goes to infinity, and we don't have a fraction, so it might already throw us off based on what we were doing last time. We had the limit as x goes to infinity of 9x squared plus x and a square root, and then minus 3x. Well, what happens if we just plug this in? Remember, we can't really plug in infinity, but we know we can do a lot of things, because if the power on x is a positive, then it's going to give us infinity. So this is like the square root of 9 times infinity, which is infinity, plus we're plugging in and we get infinity for x, minus 3, and then another positive power of x. That first property tells us that's also infinity. Well, when we do infinity plus infinity, you can still say that's infinity. It's a really big number plus another really big number is a really big number. Doing the square root of a really big number is still a really big number, so that's infinity. Minus, and then when you multiply a really big number times 3, it's still a really big number. And you'll notice this is that other sort of indeterminate form I was talking about before, infinity minus infinity. It can be anything. So we've got to do something else. What is that something else we're going to do? Well, there's kind of 2 ways to do it. I think the better way is, especially when you have a radical here, what you want to do is rationalize. Even though it's not already a fraction, you want to rationalize it. You can make it into a fraction by doing that. Okay, so what you can do is think about this entire thing being over 1 and then rationalize. And we know when we rationalize, what we're going to do is we take what our radical portion is and we change the minus to a plus, or if it's a plus, change it to a minus. We got the square root of 9x squared plus x, then plus 3x. And what we do to the top, we must do to the bottom. So I'm going to multiply the bottom by this as well. Right? And the denominator, since it was originally 1, it's just this new thing that we're rationalizing, multiplying by. So it's the square root of 9x squared plus x, and then minus 3 plus 3x outside. Now, when we rationalize, we FOIL this. And then when we do the first, the radical parts make each other cancel out. We just get 9x squared plus x. When we do the outers, we get plus 3x times the square root of 9x squared plus x. It's going to be a big numerator, so I'm going to go ahead and extend it. When we do the inners, we get negative 3x times the square root of 9x squared plus x. And then when we do the last, negative 3x times 3x is negative 9x squared. Now remember, if you rationalize and you do it properly, a lot of things should cancel out. The radical portions immediately go away because we have positive 3x and negative 3x multiplying the same radical. But also the 9x squared and negative 9x squared cancel out. This entire numerator is just x. And then we got the denominator down there. Square root of 9x squared plus x plus 3x. Now, this isn't something that we can just plug in because this looks a lot like the previous ones. We have a fraction, we're going to infinity. If we plug it in, we're probably going to get infinity over infinity. We want to multiply by the largest power of x this time. And just like the previous one with the radical, you have to be careful. Because the largest power of x inside the radical is 2, and the largest power outside of x is 1, they're actually just x because the square root of x squared is x. That means the largest power of x is 1. And the way we're going to write it, what we're going to divide by the largest power of x is just x. So I'm going to divide everything by x. Now that I have a fraction, I can divide the top and bottom by that. At the beginning, I could not divide the top and bottom by the large power of x because there really wasn't a bottom. And if I did, nothing would work out for me. There's not a fraction. All right, so I'm going to continue this down here. We have the limit as x goes to infinity. We have x over x on the top divided by, remember when we throw the x in the square root, it's going to become x squared. That's what that's saying. So we get 9x squared over x squared plus x over x squared, because it's in the square root, plus 3x. This one's not in the square root, so it's just over x. And now we cancel and simplified. X over x is just 1. The 3x cancels out with 3x there. The x squareds cancel out right there. And here we have x canceling out with one of the x squareds on the bottom, so we get 1 over x there. Now go ahead, just write in the one step before you plug it in to clean it up, make it a little easier for you to plug in and go. We've got 1 on the top. We have the square root of 9 plus 1 over x on the bottom, and then plus 3 on the outside of the square root. And when we know when we do the limit as x goes to infinity, the only x in the problem is right here. And that's 1 over x. That becomes 0 when we take the limit. And we're finally going to have our answer. We have 1 over the square root of 9 plus 0 is 9, square root of 9, which is 3. And 3 plus 3 is 6. So we did all that work and we figured out the limit is 6, 1 over 6. I'll go ahead and mention that this is definitely a more challenging problem, because you pretty much have to make it into the more challenging form first, and then do that. Do the challenging part. Now, one thing you could maybe have noticed here, especially when you get used to these, is that you may have noticed that the largest power of x on the top and the bottom is the same, because the square root of x squared is like x. But you'd have to be really careful because the coefficient here is 1. The coefficient on the bottom isn't 9. It's not the square root of 9, and it's not just 3. It would be the square root of 9 plus the 3. So in general, when you have radicals, I recommend not even trying to do the shortcut that we talked about above, just as a warning. All right, number 5 here. This one looks a lot different than maybe the other ones because we have e, but it's not going to be bad at all. we're going to just follow the same general strategy. It says we want to do the limit as x goes to infinity of 1 plus e to the 2x over 3 minus e to the x. Well, we want to still divide by the largest thing. The thing here is not a power of x, though, it's e. And this one is specifically, you could actually do e to the x or e to the 2x because of our exponent rules. And I'm going to divide everything by e to the x. But before I do that, let me explain why this is good enough. It's good enough because e to the 2x, you have exponent rules that tell you when you're multiplying, what you're really doing is reversing, doing exponents to exponents. So I can first rewrite this as e to the x times 2 because that's just reordering the order of multiplication. But now this is the same thing as e to the x squared. And really what I have here is I have e to the x. Yes, it's being squared, but it matches the e to the x down there. So let's go ahead and see how this is all going to work out. Actually, it might be easier just to divide by e to the 2x, just to match up with what we're doing before. We could do e to the x, but I'm going to divide by everything by e to the x squared, e to the 2x, just to really match it up, make it not feel like it's a different kind of problem like the ones we were doing with just powers of x. All right, so let's go ahead and do that. We got the limit as x goes to infinity. We got 1 over e to the x squared plus e to the 2x is e to the x squared. That we just figured that out. That's why we're dividing it by it. E to the x squared. And then that's over 3 over e to the x squared minus e to the x over e to the x squared. All right. And how are we going to finish this one up? Well, what you might be wondering is we don't really have a rule for doing the limit with e to the x. We don't have a 1 over e to the x. And you're right, we do not. But we know what the limit of e to the x is as x goes to infinity. That's actually infinity. So what you want to do is simplify like we did before. E to the x squared over e to the x squared cancels. So this is just 1. One of the e to the x's cancels with one of the e to the x's down here because this is e to the x times e to the x. So we have 1 over e to the x there. And let's go ahead and plug it in. We've got 1 over e to the x squared plus 1 over 3 over e to the x squared minus 1 over e to the x. All right, and what are we going to get here? Well, now you can do the limit of each part. And I'll just recall from above, you should be looking at that limit, the special limits at infinity, the limit as x goes to infinity of e to the x is infinity. So when we do this limit as x goes to infinity, this would be infinity. Infinity squared is still infinity. I'm going to write 1 over infinity plus 1. I'll put it in quotes because we can't really actually say 1 over infinity, but I want to explain what this simplifies to afterwards. And then this is 3 over, this is also infinity. Squared doesn't matter, it's still infinity. Minus 1 over another infinity. Okay. And what is a number over infinity? Well, it's actually 0, because when you divide something by a really big number, you get 0. That's actually what the 1 over x to the n being 0 means. So what you could do, just to maybe convince yourself of that, is just do 1 over a number. But if you keep adding zeros to it, notice that scientific notation, this means it's 1, but it has 19 zeros before the decimal point, after the decimal point, before we even get to the 1, it's basically 0. So all of these are 0, and we have 1. 0 plus 1 over 0 minus 0. And then we get 1 over 0, which is once again, plus or minus infinity. And we've already established how we determine which one it's going to be. From the previous example, let's go ahead and do that. We know what we got to do is plug in a big number because we're going towards infinity into this and see which one it's going to be. Let's say we got 1 plus e raised to the 2 times, let's do 1,000, divided by 3 minus e raised to the 1,000. Now, because I chose such a big number and these are exponential, it's going to be a huge number. But the main thing you want to notice, this is in scientific notation, it's negative. This is a negative number, which means it's going to be negative infinity. Okay, so this limit is negative infinity. Let's go ahead and just write that in here. If you were asked to specify negative infinity or infinity, you would do it like that. However, for the purposes of us, we only really want D and E. Okay. All right, so this video is actually getting a little longer than I had hoped, so I'm going to stop here. The next video, I will definitely finish up this section.